As we talk about resonance structures, we're going to use electrostatic potential maps. Electrostatic potential maps are just a really useful way to illustrate the distribution of charge along a covalent bond. And so it shows the relative charge. More positive areas are blue, more negative areas are red. If we have an area with very little positive or negative, it tends to come up as green. For example, look here, this is hydrofluoric acid. We see here that the fluorine here is very electronegative, so it pulls those electrons towards itself. And so you can see there's a lot of electron density here. We have a partial negative to show that. And then here we have a partial positive, right? And it shows, because those electrons are pulled away, that more positive region here in blue. This is methane. It's a nonpolar molecule. While there are a little bit of difference in the electronegativity between the carbon and the hydrogen, you can see here how it's mostly a nonpolar molecule. There's not a strong concentration of positive or negative charge. And so those are just really interesting, I feel like, to compare. So let's talk about resonance theory for just a second. Sometimes what you're going to see is some species are not really going to be described well by Lewis structures. And the reason for that is that Lewis structures imply that electrons are localized or confined to a specific region in space. In reality, electrons are spread out or delocalized in some molecules. So, for example, I want you to look at this molecule, which we drew the Lewis structure for on a previous screencast. We have a double bond here, a single bond here, a negative charge, and a formal charge of 0 here. Okay, and so when you look at the structure, what you would expect is there to be a difference in these two oxygen atoms. But what we find is there's an identical charge on the oxygen atom. So instead of these electrons being localized or really fixed on this oxygen, what we find is that they are spread out or delocalized across this bond and this bond. Okay, these are identical CO bonds, and that indicates that those electrons are spread out. So these are called, this structure would have a resonance structure. And we come over here and we look at resonance structures. Resonance structures differ only in the placement of their valence electrons, not their atoms. And so resonance occurs when there are two or more valid Lewis structures. We can see these are two valid Lewis structures here. So resonance occurs when there are two or more valid Lewis structures. And we see that here. Okay, for the molecule that we looked at, we could see one valid Lewis structure here and another valid Lewis structure here. These are called resonance contributors a lot of times. And then what we find is that this doesn't actually exist in a bottle, and this doesn't actually exist in the bottle. It is maybe a mixture or an average of the two. So if we have these two resonance structures and we were to take the average, this is how we show it. We show the bond spread out over where those electrons are delocalized. Where each resonance structure had a negative charge, we then say we have a partial negative here and a partial negative here. So I want to give you some kind of words to write here, some definitions, as we kind of go through this. There we go. So this is a resonance hybrid, right? And a resonance hybrid is just a composite of all the resonance structures, right? Now, the resonance hybrid looks like the lowest energy or most stable resonance structure. The two resonance structures that we see here are what we call equivalent. As a result, each structure is going to contribute equally to the resonance hybrid. And we're going to talk more about resonance structures that are equivalent or non-equivalent in a second, so don't panic on me. That being said, it's really important to understand that resonance provides stabilization. And all else being equal, the greater number of resonance structures the greater the resonance stabilization. So when we talk about resonance structures, these not actually existing in the bottle when you go and pick up this chemical, what we find is that the resonance hybrid is what actually exists. And for me, when I was a student, this really rocked my world. And so I love this analogy. So we have a unicorn and a dragon, and these are resonance contributors. And so they are these two molecules. These two things are fictitious. They don't actually exist. These two molecules are fictitious. They don't actually exist. But if you were to blend these two together, what you would find is that you would have maybe like a rhinoceros, which does exist. And so this molecule does exist. It's a blend of these two Lewis structures. So let's talk about what do you do in cases where resonance structures are inequivalent. When this occurs, the relative energies must be determined in order to obtain their relative contributions to the hybrid. A resonance structure is lower in energy or more stable when it has more atoms with a completed octet, right? Fewer atoms with non-zero formal charge, and then if it's got a negative charge on the more electronegative atom, or a positive charge on the more electropositive atom. So I want to do an example. And before I do an example, I want to emphasize that these are listed in orders of importance. So if the first one here is more important, in case there's a conflict. Okay, so let's do an example. We're going to look at these two resonance structures, resonance contributors. And so we want to figure out which one is the major contributor and which one is the minor contributor. So which one contributes the most to the resonance hybrid. And so if you're asked a question like this, you just need to kind of go through and think about it this way. The first thing you need to ask yourself is which one has more octets, right? And so we're just going down 1, 2, and 3. So when we look at and compare this molecule to this molecule, we see that this molecule here on the right has more octets. This carbon does not have a completed octet, so it lacks an octet. So the one with the more octets is the one on the right. And then we're going to ask ourselves the next question, right? Which one has a non-zero formal charge? And the answer is neither, right? Both have a positive one formal charge. So we can't use that to discern which is the major contributor or the minor contributor. So the next question we would ask ourselves is which one has the positive one charge on the least electronegative. Right? And so when we look at this, we'll compare the electronegativity of the carbon and the oxygen. And carbon is less electronegative than oxygen. And so that would be the one on the left. Now, here's the deal. That's a contradiction. We have one of this criteria that says this should be the major contributor, and this criteria says this should be the major contributor. And so when you look at that, then you have to weigh importance. And the one with the most octets, that factor is more important. So the right here is the major contributor. And the left here is the minor contributor. Right? Now, we can have, as I mentioned, equivalent resonance structures. A species that has equivalent resonance structures tends to be very highly stabilized. And as the number of resonance structures increases, the species tends to be more stable. This is resonance contributors of benzene. This is the resonance hybrid. I want you to notice there's no charge in benzene, so we're not showing any partial negative or partial positive charges here. These two are equivalent. They contribute equally to the resonance hybrid. When we talk about non-equivalent resonance structures, right, and we compare this one, and we look at our criteria, both have molecules with completed octets. This has a charge, right? This one doesn't. So only the one here on the left contributes significantly. So that's the major contributor. Right? So again, that's just another example of using that criteria. Now, one of the things that you're going to be asked is to draw resonance structures. When we draw resonance structures, right, it's important to remember that any two resonance structures are only different based on where the electrons are located. So the atoms themselves remain frozen, okay? And then we represent the movement of electrons by using curved arrows, okay? And these curved arrows are showing the movement of a pair of valence electrons. And so what's happening here is the electrons that make up this bond, the double bond, one pair is moving up here to be on the oxygen, and now there's an additional lone pair here on the oxygen, and this is a single bond. These electrons here are moving down to form a double bond here. And so now they've formed a double bond here, and there are only two lone pairs on this oxygen. Now, a curved arrow. So I want to make some notes here about these curved arrows. A curved arrow can originate, which means like it can start from a lone pair of electrons. And there's an example here where it starts from a lone pair of electrons. Or from the center, needs to be in the center of a double or triple bond, okay? And that's going to indicate that specific pair of electrons that's being moved. So notice this starts in the center of the double bond, and the arrow shows the direction they're moving in. So that means the arrow points to an atom if the electrons are being moved to become a lone pair, right? Otherwise, the arrow points to the center of an existing single or double bond, right? And that represents the formation of a new double or triple bond. Okay, so I have a list of features here that indicate that there's another resonance structure, and we're going to go through those features. There are 5 of them. So here are the 5 key features in a Lewis structure that suggest that another resonance structure exists. Here's the first feature. You have a lone pair on an atom next to a multiple bond. So we have a multiple bond here, and we have a lone pair here. And so that is a indication that we could have a resonance structure where these electrons move here and they form that double bond, and these electrons move up to be on this atom, okay? The next feature is you have an atom lacking an octet next to a multiple bond. So for example, we have this carbon here. It's got a positive charge. These electrons, remember electrons are negative, they're going to want to move towards that positive charge. And so those electrons are going to be delocalized over between this bond as well. And so you are going to see this is the other resonance contributor. I wanted to show you this resonance hybrid just to give us a little bit of practice at looking and drawing the resonance hybrid. So when I draw the resonance hybrid, I draw all of the localized, first off, I draw all my atoms, and then I draw all my kind of localized bonds and things of that nature. Then I look at where that double bond kind of travels to. And we can see the double bond starts here and then travels there. And so that means that then I'm going to show that dashed line spread out wherever that double bond is in the 2 resonance contributors. And then this carbon is partially positive and that carbon is partially positive. So I wanted to take a quick moment and just do one more of those. The third feature is that you have an atom with a lone pair adjacent to an atom lacking an octet. So this guy doesn't have a full octet. We've got a lone pair. Those electrons can jump there. And now you have this as the resonance contributor. 2 other things that we can, so 2 other features, I didn't want to put them all in one feature, is that you can have multiple polar bonds, okay? So we see an example of that here. And then you can also have a ring of alternating single and multiple bonds, like benzene, which you can see here. Now, I want to make a note here that you need to, when you're drawing these, you need to avoid drawing two curved arrows pointing toward the same atom or pointing away from the same atom. And we will practice this in class. And the best way to kind of get used to drawing these is to practice. So we have practice problems in our textbook. They're at the end of each section and the end of the chapter. You can come and you can work practice problems in my office. We're going to practice this in class as well. So it might take a second, but we're going to practice. When you are drawing all of the resonance structures of a species, it helps to approach this systematically, okay? So the first thing that I do, right, is I identify which of the 5 features the species possesses, okay? And then I add the curved arrows that the species calls for. And then I draw the new resonance structure. Right? Starting with the localized electrons, right? And then adding the delocalized. And then what I do is I examine the resonance structure. To see if it possesses, okay, there we go. I got panicked about the spelling there. Possesses one of the 5 features. So for example, when we look at this molecule, we see that it possesses feature 1, where you have a lone pair adjacent to an atom with a double bond, okay? And so what that means then is that these electrons can go here to form this double bond, and these electrons go here to sit on this atom. Now, when we examine this one, we say, oh, hey, look, we've got the same thing. And so these electrons can go here, and then these electrons go there. And we have another resonance structure here. And so now the question is, well, would we have another one? Well, we would, because these electrons, let me do that in red so that it matches. These electrons go here, right? And then those electrons would go on the atom there. And you can see that 4th resonance structure. Notice these are double-headed arrows. That specifically means a resonance structure. So make sure that you're using those double-headed arrows there. So let's do another example. We're going to draw another resonance structure of the species shown here. What we notice, we need to ask ourselves, what feature does this have? That's how we start these problems. When we start this problem with what feature, we say, look, it's got a lone pair next to a multiple bond, a double or triple bond, okay? So what we're going to see happen then is these electrons are going to move towards the multiple bond. They are going to go here, and then here's the deal. When this forms a new bond here, that means carbon would have 5 bonds. Carbon cannot have 5 bonds. So that means these electrons would then go onto that carbon. So when we draw that resonance structure, we would come here and we would draw a double-headed arrow. And then we're going to start out by drawing everything that's localized, that doesn't move. And then I'm going to follow my arrows and say, okay, I'm following my arrows, and now we've got another double bond here, and then we've got a lone pair of electrons there. And then I need to consider if there's a charge. And so I'm going to come here and I'm going to say, okay, look, with this carbon, I know that its valence electrons are 4, minus it has 3 bonds and 2 lone pairs, and I did that backwards. So 2 lone electrons plus 3 bonds, and so that gives it a -1 formal charge. And so that means that negative is right there. Okay. If we were to draw the resonance hybrid of this, we would draw in all of our localized electrons there, and then we would come here, and anywhere there that those electrons move to, so we formed a double bond there, and then we had originally a triple bond there, and then we would put the partial negatives over those carbons because they had that negative charge, and that would be the resonance hybrid. So again, like I mentioned, we will do some problems like this in class, and as always, if you have questions, please feel free to stop by my office.